Hello, I'm Roman, and welcome back to the series of the videos called Neural Networks from Scratch in Go, where we dive into what is the neural network is, how they look like, what is inside, and how we can program them manually. So I'm using this book called Neural Networks from Scratch in Python, but as you can guess from the name of the series, I'm using Golang. And the reason to this, I just want to make things more complex to myself, because it's not that interesting to just, copy paste the code and use it. And today we're going to start the next chapter that is called activation functions. And in the previous video, we did some refactoring. So right now we have the dataset and the dense layer class. So for the dense layer, we have something that is called layer with weights, biases, and the output. And we have the initialization function with the forward that actually does the computation based on the inputs and the weights and biases. And we moved our function that generates some initial data for the layers. And right now we have actually the neural network. Well, we don't have the output nodes yet, and I believe the idea of the activation function is what we're going to do with this. But again, we have the initialized data, we have it as an input, then we have the first layer, the second layer, and we can see the results. So let's check that it still works. So there are a bunch of the numbers, and all of the values are randomly initialized. So we don't have to print it again. I will delete some leftovers. And again, so let's take a look on the activation function. I hope you don't... Yeah, you should not hear the noise that I have here. So let's go. In this chapter, we will tackle a few of activation function and discuss their roles with different activation functions for different cases, and understanding how they work can help you probably pick which of them is best for your task. The activation function is applied to the output of the neuron or layer of the neurons, which modifies the output. So right now, our dense layer doesn't have any activation function with activation functions, because if the activation function itself is non-linear, it allows for neural networks with usually 2 or more hidden layers to map non-linear functions. We'll be showing how this works in this chapter. Okay, so right now, as I said before, we have only 1 input layer and 2 hidden layers, but we don't have the output defined yet. In general, your neural network will have 2 types of activation function. The first will be the activation function used in hidden layers, and the second will be used in the output layer. Usually the activation function used for hidden neurons will be the same for all of them, but it doesn't have to. Okay, so for all of the hidden layers, probably we'll use the same activation function, but probably there is something different. Recall the purpose this activation function serves is to mimic a neuron firing and non-firing based on the input information. So I guess the idea of firing means that based on the input, we can disable some neurons at all. What does it mean? It means that the multiplication using this neuron then will give you 0 value, which kind of declines or removes the whole value. The simplest version of this is a steep function. In a single neuron, if the weights multiplied by input plus bias returns in a value greater than 0, the neuron will fire and output 1, otherwise it will be output as 0. The activation function has been used historically. This activation function has been used historically in hidden layers, but nowadays it's rarely a choice. Okay, so it's actually not used that much. A linear function is simply the equation of a line. It will appear as a straight line when graphed, where x equals y equals that, and the output value equals the input. Okay. This activation function is usually applied to last layer's output in case of a regression model. A model that outputs a scalar value instead of the classification. We'll cover regression in chapter 17 and soon in an example in this chapter. Okay, sigmoid. Oh, yes. The problem with the steep function is that it's not very informative. When we get to training a network optimizers, you will see that the way an optimizer works is by assessing individual impacts that weights and biases have on the... The problem with the steep function is that it's less clear to the optimizer what these impacts are, because there is very little information gathered from this function. Well, it's actually binary. I mean, if it's a positive value, it will return 1. If it's a negative value, it will return 0. It's hard to tell how close this steep function was to activating or deactivating. Maybe it was very close, or maybe it was very far away. In terms of the final output value from the network, it doesn't matter if it was close to outputting something else. Those, when it comes time to optimize weights and biases, it's easier for the optimizer if we have activation functions that are more granular and informative. So I guess the idea of this is the value that the activation function gives can help the training process to optimize or actually change the values more efficient. The original more granular activation function used for neural networks was the sigmoid activation function, which looks like this. The sigmoid function is very interesting. You can see that it's pretty close to the 0 and it's pretty close to the 1, but it's never has the value of the 0 or of the 1. And as you can see, the far it goes with the x value, the closer it's to the 1 or, well, in the negative to the 0. But there is some part where the change of the output is very drastic. This function returns the value in the range of 0 for negative infinity through 0.5 for the input of 0 and to 1 for positive infinity. We'll talk about this function more in chapter 16. As mentioned earlier, with dead neurons, it's usually better to have a more granular approach. So you can see that with values around 0 input, it's actually the range of the changes is way bigger than, for example, between, I don't know, 100 and 1000. And I guess because, as we checked before, for example, most of the neural networks, well, at least for the initial params, they They initialize between -1 and 1. So I think this is why the sigmoid gives you the most feedback in this range. Probably that's the reason. In this case, we're getting a value that can be reversed to its original value. The return value contains all the information from the input, contrary to a function like the step function, where an input of 3 will output the same value as an output from the sigmoid function. Being in a range of 0 to 1 also works better with the neural networks, especially compared to the range of the negative to the positive infinity, and adds nonlinearity. Yeah, I think that the reason that's about the nonlinearity is this change, because this growth is linear, but this is definitely not. Sigmoid function, historically used in hidden layers, was eventually replaced by the rectified linear unit, or ReLU. Let's say it will be using the sigmoid function as the output layers activation function in chapter 16. Okay. The rectified linear activation function. Well, it looks like the linear one, except for the negative values. If it's a negative value, it returns 0 for all of them. The rectified linear activation function is simpler than the sigmoid. It's quite literally linear function clipped at 0 from the negative side. If the x is less or equal to 0, this part, then the output is 0, otherwise y equals to x. This simple yet powerful activation function is the most widely used activation function at the time of writing for various reasons. The time of writing, I mean, it's 2024. I bought this book. I'm not sure. I think the latest revision was done in the previous year, so it's pretty much up to date. While the sigmoid activation function isn't the most complicated, it's still much more challenging to compute than the ReLU. The ReLU activation function is extremely close to being a linear activation function while remaining nonlinear, due to that bend after 0. This simple property is, however, very effective. Okay, hopefully we'll see. Now that we understand what activation function represents, how some of them look, and what they return, let's discuss why we use activation functions in the first place. In the most cases, for a neural network to fit a non-linear function, we need it to contain 2 or more hidden layers, and we need those hidden layers to use a non-linear activation function. In most cases, for a network to fit a non-linear function, we need it to contain 2 or more hidden layers, and we need those hidden layers to use a non-linear activation function. Okay, first off, what's a non-linear function? A non-linear function can be represented well by a straight line, such as a non-linear function cannot be represented well by a straight line, such as sine function. For example, trying to figure out the cost of some number of shirt. And we know the cost of individual shirt, and that there are no bulk discounts, then the equation to calculate the price of any number of those products is a linear equation. Other problems in life are not that simple, like the price of a home. The number of factors that come into play, such as size, location, time, Many of the more interesting and hard problems of our time are nonlinear. The main attraction of neural networks has to do with their ability to solve nonlinear problems. First, let's consider a situation where neurons have no activation function, which would be the same as having an activation function as linear. With this linear activation function, a neural network with 2 hidden layers of 8 neurons each, the result of training this model will look like this. 1881 neural network with linear activation. Okay, so it tries to fit this function. When using the same 2 hidden layers, 8 neurons, each with the rectified linear activation function, we see the following result after training. To be honest, not clear yet, but I'm patient. Now that you can see this is in case, this is the case, we still should consider why. To begin, let's revisit the linear activation function and let's consider this on a singular neural level. Given the values for weights and biases, what will the output be for a neuron with linear activation function? Let's take a look at some example file. Let's try to update the first weight with a positive value. Okay, so example of the output with the neuron. Okay, so this is the result. As we continue to tweak with weights, updating with a negative. So here it is. But I guess it's still firing, right? And updating weights and additional bias. Okay. Example of the output with the neuron using a linear activation function updated another way. No matter what we do with this neuron's weights and biases, the output of this neuron will be perfectly linear to no matter what we do with the weights and the biases, the activation function, it will perfectly fit into the activation function, because the activation function is literally returning the input value. This linear nature will continue throughout the entire network. Okay, we have some values. A neural network with all linear activation function. No matter what we do, however many layers we have, this network can only depict linear relationship if we use. Okay, so it can. Oh, okay. So the main goal of the neural networks is to solve nonlinear problems. If we're using the linear activation function, that it can understand only linear dependencies, well, between the input and the output. I guess that's my assumption right now. It should be fairly obvious that this will be the case, as each neuron in each layer acts linearly. So the entire network is a linear function as well. Okay. Okay, let's take a look at the real loop. We believe it is less obvious how, with a barely non-linear activation function like the rectified linear activation function, we can suddenly map non-linear activation relationship with functions. So now let's cover that. Let's start again with a single neuron. We'll begin with both of weight of 0 and the bias of 0. Okay, 0 and 0. Single neuron with single input is 0 to weight. Okay, so it's here. In this case, no matter what input we pass, the output of this neuron will always be let's set weight to be 1. Okay. So it will hit this one, right? Now it looks just like the basic rectified linear function, no surprises yet. Now let's set the bias to... Okay, so if the input is 0 plus bias... Oh, I mean, we will start to activate with the value of minus 0.5. If we have the minus 0.5 multiplied by 1, it will be this point, and then plus it equals 0, so it will activate from here. We can see that in this case, with a single neuron, the bias offset the overall function's activation point horizontally. By increasing bias, we're making this neuron activate earlier. What happens earlier? I mean, I guess, meaning earlier on the scale of positive and negative numbers. What happens when we negate the weight -1? It's going to be mirrored. So it means that this neuron will be activated for all the negative numbers up to 0.5 positive value. I'm still not sure how it has effect on the neural network, but let's see. With the negative weight and this single neuron, the function has become a question of when this neuron deactivates. Up to this point, we have seen how we can use the bias to offset the function horizontally and the weight to influence the slope of the activation. So it's -1, but imagine if it will be -2. I think so it will be something like this. Yeah, if it's -100, then it will be like pretty vertical. Moreover, we are also able to control whatever the function is once we determine where the neuron activates or deactivates. What happens when we have, rather than just one neuron, a pair of neurons? For example, let's pretend that we have 2 hidden layers of 1 neuron each. Thinking back to the linear activation function, we unsurprisingly discovered that the linear activation function produced linear results, no matter what chain of neurons we made. Let's see what happens with the rectified linear function for the activation. Oh, okay. So with the linear activation function, there is no such thing as firing and a non-firing. Okay, we'll begin with last values for the first neuron of weight 1 with a bias of 0 and the second neuron. So I think this is the second. Oh, this is the first one. As we can see so far, there is no change. This is because the second neuron's bias is doing no offsetting, and the second neuron's weight is just multiplying output by 1. So there is no change. Oh, because there is no... Let's try to adjust the second neuron bias right now. Pair of neurons with a single. Now we see some very interesting behavior. The bias of the second neuron indeed shifting the overall function, but rather than shifting it horizontally, it's shifting the function vertically. What then might happen if we make the second neuron weight -2 rather than 1? So, I mean, the function is the same, but the way each neuron uses that function is influenced by the weights and biases. And I guess okay, here's the deal. We have some inputs, we have some outputs, and we have the random weights. And I guess the idea of the neural network is to get those numbers of the weights and biases using the activation function to take the input and feed the output data as close as possible, right? When both neurons are activated, when there is area of effect comes into play, pair of neurons with single inputs and real activation function area of objects. Okay, so it activated here, then it activated here, so the whole activation is here. Now let's take this concept and use it to fit to a sine wave function using two hidden layers. We'll do this by working with one pair of neurons at a time, which means one neuron from each layer individually. For simplicity, we're also going to assume that the layers are not densely connected, and each neuron from the first hidden layer connects to only one neuron. Okay, so it's not the dense, meaning that there is an input, then first node, then the second node from the second layer, and the output. That's usually not the case with the real models, but we want to this simplification for the purpose of the demo. Additionally, this example model takes a single value as an input, the input to the sine function and an output to the single value. Okay. To start, we will set all weights to 0 and work with the first pair of neurons. Okay, next we can set the weights of the hidden layers and the output neuron to 1, and we can see how this impacts the output. Okay, 1 weight by 0, 1 weight by 0, 1 weight, so it's pretty linear. In this case, we can see that. Okay, so we're trying to fit the model to this function. We can further increase the slope by adjusting the weight for the first neuron of the first layer to 6, but we can see now, for example, that the initial slope of this function is what we would like, really? Okay, But we have a problem. Currently this function never ends. This function never ends because this neuron pair never deactivates. We can visually see where we would like the deactivation to occur. It's where the red line, it's where the red fitment line, our kernel, diverges initially from the green, I guess here. So now while we have the correct slope, we need to set this spot as our deactivation point. Okay, so now while we have the correct slope, oh, okay, so I guess it should fit the whole. Okay, so in the end we should have the combination of the weights and biases that based on the input value, the output value will be as close to this green line as possible. But instead going through the function itself, it will go through the neural network. To do that, we start by increasing the bias for the second Now I would like to flip the slope back. How might we flip the output of these two neurons? It seems like we can take the weight and then I guess we're going to move it up. We're certainly getting closer to making the first section fit how we want. Now all we need to do is offset this up a bit. For this hand optimized example, we're going to use the first 7 pairs of neurons in hidden layers to create the sine waves shape, then the bottom pair to offset everything vertically. Okay, so this will offset it vertically. At this point we have completed the first section with area of effect being the first upward section with the sine wave. We can start on the next section that we wish to do. We can start by setting all weights for this second pair of neurons to 1, including the output neuron. The second pair to start influence output. So we want to adjust the function horizontally. As you can recall from earlier, we adjust the first neuron's bias in the neuron pair to achieve this. Also, to modify the slope, we'll set the weight coming into that first neuron for the second pair setting to 3.5. This is the same method we used to set the slope for the first section, which is controlled by the top pair of neurons. After this adjustment, okay, so 3.5 is this slope, I guess. This slope is... no, that's a different one. Right, wait, where is it? Yeah, so that slope is 6. This slope is 3.5. We will now use the same technology as we did with the first pair to set the deactivation point. We set the weight for the second neuron in the hidden layer pair to -1 and bias to... okay. Then I guess we need to flip again with -1 here. Okay. And just like with the first pair, we will use the bottom pair to fix the vertical offset. Using the bottom pair of neurons to adjust. Okay, so this pair will be changing to adjust. We then continue with this methodology. We will leave it flat for the top section, which means we will only begin the activation for the third pair of hidden layers. The process is simple, repeated for each section, giving us the final result. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We can then begin to pass data through to see how this neuron's area of effect come into play only when both neurons are activated based on the input. Okay, so we pass this data to each neuron, and the only thing I don't understand is when the first neuron is not activated, the second one is activated. Okay, so this one goes here and returns in this. If we enable all the weights now and allow a mathematical optimizer to train, we can see even better fitment. Okay, so this is what the neural network will produce for the input value as the output. Animation for the entirely of the concept of neural fitment. It should begin to make more sense to you how more neurons can enable more unique areas of effect, why we need two more hidden layers, and why we need non-linear activation functions to map non-linear problems. For further examine, we can take the above example with 2 hidden layers of 8 and instead use 64 per hidden layer, seeing the even further continued improvement. So this is pretty good. I see there are some steps. Okay, the reading took already 18 minutes. Okay, let's take a look. Okay, so this function is the result of 2 functions, like this one and this one. Hmm. Hmm. Okay, so it tried to replicate this slope. Okay, so this is the adjust. And this is the first pair. Then comes the second pair. This is two fully connected hidden layers of 64 neurons each with the rectified linear activation function. Okay. Despite the fancy sounding name, the rectified linear function is straightforward code, most closely to its definition. So it takes the array of inputs and it checks for each input. If it's greater than 0, then it appends the value, otherwise it appends 0. Okay. We made up a list of values to start. The ReLU in this code is a loop where we check in if the current value is greater than 0. If it is, we're appending it to the output list, and if it's not, we're appending 0. This can be written more simply. Yeah. Compile contains an equivalent np maximum. Okay. This method compares each element of the input list or an array and returns an object of the same shape filled with the new values. We'll use it in our new rectified linear activation class. Activation ReLU. Okay, so it takes the input and okay, so it's not a layer. So it's activation and will be ReLU. Yes. Package. Structs active. What I use here? Dense. We have the struct, and then we have dense activation forward, and as an input we take, well, actually we take okay, inputs. Oh. All right. Okay, so we need to go over. Actually, interesting. Do we have the real metrics and statistic probability optimizing network creation? As benchmark, activation, no. Oh, but can I search? Oh, documentation. Loss. I need math, probably. Max. Okay, let's implement it in a simple way. So that will be, well, first I need to create the outputs, and it will be math dense unused write. Then we go add okay, or I then if value greater than 0, duration output set value, right? Else like this, right? So then okay, I will remove it for now. Main activation, and then we create an activation. Real one activation relu, right? Then we do forward, and it takes layer 1 output, and then we should be able to print this. Oh, wait. Okay, let's test it. No, stop. Okay, so it changes something, right? Yeah. Okay, that was the problem, because I was writing into the copy of an activation, but not into the activation itself. And if we take a look, we can see that some of them are 0. There are actually a lot of the 0 values, and some of them, and the rest of them, are positive numbers. But here we can see that there were a lot of the negative numbers. Okay, so forward pass through the activation function takes in output from the previous layer. So for example, if we will go for the next layer, then for example, what we should take is output as input for layer 2. Right? As you can see, negative values have been clipped, modified to be 0. That is all there is to the rectified linear function activation used in the hidden layers. Let's talk about the activation function that we're going to use on the output of the last layer, the softmax. Okay, I will stop here for today, as that was already a lot of the information, but we checked several activation functions. We deeply took a look at how the rectified linear activation function works, and we actually implemented this with the code. Not that much code, but I think that's important step to understand how the neural networks work. Thank you for watching, and I see you tomorrow. Bye bye.